This is motor action potential to muscle contraction. So TTBs are extension of plasma membrane in contact with the sarcoplasmic reticulum. These are the TTBs. They are extension of the plasma membrane. This is the plasma membrane that covers the muscle. Okay. In contact with the sarcoplasmic reticulum, allow for coordinated contraction of striated muscles. So this is the sarcoplasmic reticulum. It is in contact with it, allows for coordinated contraction. Action potential opens presynaptic voltage-gated calcium channels, including inducing acetylcholine release. So the action potential from the nerves here releases calcium and allows calcium in and releases acetylcholine, opening presynaptic voltage-gated calcium channels. These are the presynaptic voltage-gated calcium channels, inducing acetylcholine release. Okay, and acetylcholine will go to the postsynaptic acetylcholine binding site. So postsynaptic acetylcholine binding site leads to muscle cell depolarization at the motor end plate. So this is the motor end plate. This is the muscle cell depolarization. Depolarization travels over the entire muscle cell and deep into the muscle via the TTP. So depolarization will travel over the entire muscle. So you see it goes like that, entire muscle. Over the entire muscle cell and deep into the muscle via the TTPs. The way that it goes deep into the muscles by the TTPs. Membrane depolarization induces conformational changes in the voltage-sensitive dihydropyridine receptors (DHPR). So the depolarization will make conformational changes in these receptors, which is the dihydropyridine receptors, and is mechanically coupled Ryanair receptors. These are the Ryanair receptors. What are these changes? So calcium release from the sarcoplasmic reticulum. It will lead to calcium release from the sarcoplasmic reticulum, buffered by calsequestrin into the cytoplasm. So the main goal is to release this calcium from the cytoplasmic reticulum into the cytoplasm of the muscle cell. Tropomyosin is blocking myosin binding site on the actin filament. Release calcium bind to troponin C, shifting tropomyosin to expose the myosin binding site. So we said that the main goal is releasing this calcium from sarcoplasmic reticulum. Why? Because this calcium will go to the muscle fibers. Filaments. So the calcium will go to the muscle, and here it is. The calcium will bind to troponin C. This is the receptor that it will bind with, and when it binds to troponin C, it will shift tropomyosin, as tropomyosin is blocking the myosin binding site on the actin filament. This is the myosin and this is the actin. When calcium binds to troponin C, it will shift tropomyosin. See here, the tropomyosin, this is the green thing covering the binding sites, which is the blue dots. When calcium binds to troponin C, it will shift the tropomyosin, exposing the binding sites. And by that, the myosin will bind to the binding site. Okay, here it cannot bind because it's covered. Okay, so myosin head binds strongly to actin cross bridge. PI released initiating power stroke. So after binding, you have to start the action. How will that start? This will be released. The PI, which is the phosphate, okay, will be released, initiating the power stroke. So when it was released, you'll see the muscle moved. During the power strip, force is produced as myosin pulls on thin actin. Muscle shortening occurs with shortening of the H-I bands and between Z lines. H high and wearing shorts. The A band remains the same length. A band is always the same length. ADP is released at the end of the power stroke. So yeah, when the power stroke began and the myosin pulled in the actin filaments, the changes that are seen on the sarcomere is this is the Z line, and these are the thick filament of the myosin, and these are the thin filaments of the actin. Okay, so what happens is the myosin will start pulling on the actin. Okay, so the myosin fibers will go this way. So this, the distance from the two Z lines, which is called the sarcomere length from Z line to Z line will get shorter. Okay, and the I band will also get shorter because the I band is the area where myosin is only there. There's no, where actin is only there. There's no myosin. So when you pull, this will get shorter. That's all. A binding of new ATP molecules, detachment of myosin head from actin filaments, calcium is sequestered. So we finished the contraction. We want to end this. How do we stop the myosin heads from binding to actin? We said that to initiate the power stroke, it gave away 1-phosphate. So in order to stop that, the attachment, a new ATP molecule should be present. So ATP hydrolyzes into ADP and pH and PI. Why do we need this? Because it has the PI, and PI is responsible for relaxation. That's how I think about it. So PI is for relaxation. When you lose it, you contract, and to order to relax again, you have to get it again from the ATP. Okay, adenosine triphosphate. So ATP hydrolyzed in ADP and PI result in myosin head returning to high energy position, which is cooked. Okay, yeah. So it bound here. So after it bound, the myosin head left the actin filaments and it will return to the cooked state, which is the high energy position. The myosin head can bind to a new site on actin to form a cross-spread if calcium remains available. So yeah, what's driving this process is the calcium. So whenever calcium is there, the process will keep on going. Okay, you have to know in this let's just continue it. The myosin head can bind to a new site. Okay, the uptake of calcium by sarcoendoplasmic reticulum, calcium ATPase circa must lead to muscle relaxation. Okay, in order to stop this cycle from going, you have to reuptake the calcium. How? By circa. This is the circa, sarcoplasmic whatever. The circa, which is the sarcoendoplasmic reticulum calcium ATPase. Sarcoendoplasmic reticulum calcium ATPase will take the calcium from the cytoplasm back into the sarcoplasmic reticulum, which will lead to muscle relaxation. This is so easy. All you need to know is the everything is easy. So calcium, acetylcholine, depolarization, the hydroperoxy receptor, mechanical component receptor, calcium release from cytoplasmic reticulum. Calcium will go to the myosin, will bind to troponin C, moving away the tropomyosin, allowing the myosin head to bind to actin, which this is the cross bridging. In order to initiate the power stroke, you have to lose this phosphate. It will pull into the muscle, and then this is the contraction. And then in order to relax, you need ATP to get that PI again. And when you get it, the myosin head will detach, and calcium is the driving. So in order to relax all of that calcium has to be absorbed again into the cytoplasmic reticulum by sarcoendoplasmic reticulum calcium base channels in the cytoplasmic reticulum, and that's all. Nothing is hard in it. This is the myosin filaments. These are the actin thin filaments. These are the thin line, the length of the sarcomere, and in contraction, this is the line. The length will decrease with the sarcomere. The myosin is always as it is, and the M line too, which is the middle of the myosin, has all, and the I band, which is the area that is free of myosin and only has actin, will get shorter. That's all.